Okay, so here's the answers to your questions for 8 through 10. So 8 says draw a large obtuse triangle and construct an inscribed angle. So number 8 is straightforward. It's just construction number 11. But I'll show it to you. So it says create a large obtuse triangle. So, well, clearly I need an obtuse triangle. So obtuse triangles start off with an obtuse angle. Doesn't say how specific angles, but there's my obtuse, and I guess your definition of large and mine might not be the same, but there we go. And then construct a or put a circle, inscribe a circle. So this is straight up construction 11. So remember, construction number 11, I'm not going to do it. I'll just talk you through it. You pick two of the vertices and you make angle bisectors. So I'm not going to actually do the construction, but I'm just kind of hand drawing this one. But we do the construction where we make the angle bisector. Remember, that's where you make the arc. And then from these 2 points right here, you make your intersections. And where they intersect, that's your angle bisector. And they do the same thing for another angle. I'm just kind of looking at this and kind of eyeballing it. But they want you to do the actual construction. So you're just looking where the two intersect. And from this point right here, you drop a perpendicular straight down to either one of the three sides. Measure that little section right there. That's the radius to draw the circle around the whole thing. Okay. So that's just hand talking you through doing it. So remember, it's two angle bisectors. Where they intersect, drop a perpendicular to any one of the three sides from this point right here. That is your radius to make the inscribed circle. Okay. So that is that's number 8. All right, what's number 9? Number 9 is draw a circle, inscribe an equilateral triangle in the circle. Okay, I'm just going to tell you that there are lots of ways of doing this. I don't know which way is best. I'll show you a way. This is question starts section B, so these are supposed to be hard. So here's my thoughts. Well, my thoughts is, well, it says draw a circle. So clearly we're going to start with a circle. So I'll start with a circle. I'll say this, and I already screwed this up. When you start your circle, don't do what I just did. Always draw a point first and then draw your circle. Because even though there's going to be an indentation of where my pointy part fits, I can kind of see it here. It's just easier if you start off with that point. So here's my thoughts. If I draw any line through the center, that's going to be a diameter. So I'm going to suspiciously put my diameter, I don't know. Actually, it doesn't really make a difference. But I'm going to draw a diameter. And here's my thought. So an equilateral triangle, I can construct an equilateral triangle pretty easy. So if I can start off the side, I'm just going to make an equilateral triangle over here. It's not going to be the one that's going to be the answer. So if I make an equilateral triangle, I start off with a side distance of any distance. If I measure that distance, that's going to set up the fact that anywhere along this distance now is the same length as the other side. And if I draw an arc there without changing the distance and I make the same arc over here, where these two arcs intersect is the same distance as the bottom. So if I connect the dots, I've made an equilateral triangle. And an equilateral triangle is a 60-60-60 triangle. That means this angle is 60, this angle is 60, and the other one angle is 60. Now, suppose that we dropped a perpendicular straight down, which we could through a construction, right? Through a point, not on a line, draw a perpendicular. I forget the number construction. It's 4, 5, or 6. Drop a perpendicular straight down. And since it's perpendicular and it's it's an isosceles triangle as well, that means it cut this angle in half. It's an angle bisector, which means that this angle is 30 degrees, which I could measure, by the way. Now watch this slick idea. So if we were to measure this angle right here, this 30-degree angle, and construct it onto this segment right here, so that this side right here would be 30 degrees. I'm just freehanding this. But we could do that. We could copy that and make that 30 degrees, right? Well, it turns out that therefore we're basically doing this triangle. Sorry. We're basically making this triangle right here. Go to the other side and also make it 30 degrees. and you've now made a 60-degree angle, right? So if this is also 30 degrees, then this one is this one, the whole thing is 60 degrees. So if the whole thing is 60 degrees, right, it's an inscribed angle, right? So that means the other side is 120. And since these two sides are the same, well, that leaves 120 here and 120 here. And that's your, all I have to do now is connect the dots right here. And I've made an equilateral triangle. Now I freehanded that. You'd have to do that precisely in order to get it to be exactly. I mean, it's pretty close, but it's not exactly. But that's the basic idea. The basic idea is we just set right here an isosceles triangle. This side and this side were exactly the same because it's 30. Right? You can take your compass and you can measure that if you want to. Therefore, it means that the base angles are congruent. If the base angles are congruent, well, they're inscribed as well too. And since they're equal to each other, and we know the bottom is 120, because 30 plus 30 is 60, double 60 is 120. And since this angle and this angle are congruent, that means that's 120 and that's 120. Well, if those are 120 degrees, then the angle is half of that. The angle is 60. So this is 60 and this is 60, and you've made your equilateral triangle. That's my thought. There are other ways, but that's what I would do. So the way is draw a circle, make a diameter, make an equilateral triangle, drop a perpendicular, find 30 degrees, and make 30 degrees on both sides of the diameter. Just copy the angle over, and then all you have to do is you don't have to actually draw all these angles or draw all these arcs or anything. You just need to connect this point to that point, and you've got your equilateral triangle. Okay. What else do we got? The last one, number 10, draw a circle, inscribe, a square. Okay. I'm going to use the same trick. Same trick as I did the previous time. I'm going to put a square inside of a circle. So we start off with a circle. Just trying to not make too large of a circle. Oh, I just did the same thing I just warned you against. All right, so now I'm going to follow my own medicine, and I'm going to put a dot to start off with, so it's not slipping around. Okay. So now I know exactly where the center is, so I can draw the circle a little bit easier. Okay. So here's my thought process. Same as the previous one. This is kind of a tricky, or a little trick, I shouldn't say tricky. But if I draw a diameter, okay, I got a diameter. If I draw a line that's perpendicular to this point right here, to this line, right, I'm freehanding this, but you'd have to do the actual construction. Well, that would mean that this is at 9 degrees, and wait a minute, if that's 90, now it's a central angle, which means this side is 90, or this arc, that arc is 90, this arc is 90, and this arc is 90. And if I connect the chords right here, that one, to this one, to this one, to this one, well, let's see what we made. If I look at this angle right here, it makes a diameter, so therefore this is 90 degrees. And then I can do that same thing all around, right? That means that this side is 90, or this angle is 90, this angle is 90. So now I at least have a rectangle. The very question is, do I have a square? And I do. Well, how do I know that? Well, lots of different ways. I could prove that all these triangles are congruent. I could measure the sides with my compass to, I don't know, do indirect proof. It wouldn't be exact proof. We're just measuring. One, that's that distance, that's that distance, that's that distance. Hey, it's a square. But I mean, there's other ways of doing it as well too. The other thing, you could rely on the properties of a square. We know that for a square, the diagonals are perpendicular. And then, like I said, probably the longest way would be to prove that all three of these triangles are I'm sorry, all four of those triangles are congruent, so therefore the side. So I mean, I can do that really quickly. Hey, all of them are 90, right? So there's an angle. We know that this is a radius and this is a radius, so there's two sides, so they're SAS, and all of these are all radii. So by SAS, all four of these triangles congruent, so therefore by CP, that side, so congruent, 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 congruent. So now I have a shape where all the sides are congruent, and I have four right angles. There's your square, and that would be the proof of that right there. Okay. Are there other ways of doing it? I'm sure there are, but that's the one that struck me as being the easiest way to do it. All right. So hope that helped. And that was your last question.